I'm not sure. Yeah, I couldn't tell you.
Only electromagnetic.
I could see launches from my family room.
Oh, nice.
I just look
That's
out the
really
window
nice.
and I see them above my neighbor's roof.
Or now mechanical.
Oh, and well, I'm retired now, and I took up photography when I retired, and I'd be there with my camera for every launch. That sounds like fun.
Yeah.
That's what we didn't have. So really, now we're there. Like, we're right in home. So that's good. The drawback is the fact that Linda had a lot of experience. When you're a cadre, took the whole clip. The only person in the world I've ever seen do that. And she's got the data block.
Right.
It was a little very clear. Right, I have a building.
She had a couple. Yes, she's got the key.
Oh, that's us.
He's triggered on that. If she had suppressed all of that.
Refreshment sheet, actually. Although I must tell you, copies is on the solar here. But you know what? I like to make sure
I did it down, so you know, here.
Let's go home. Well, it's like, yeah. I'm really.
Yeah, that's all.
Everything changes with age. It's clear, just a little. Let's just.
She looks to get stuck with her number. That she needs to. All right,
Yes.
let's go. Right. Here's for the next.
Well, we did this happening with that, you know, no, I mean, it's like, oh, all right, I was supposed to be safe. And I'll take it.
Yeah, we might. This part of the box. Yeah, okay.
Okay. I don't want
Hey,
to.
Doc.
It's gonna be good if you talk. Good turnout.
Don, I think you may have introduced an echo.
Yeah, something just
I think I
happened.
stopped it. Right, I'll get it. Just go ahead. Look at my settings.
We're not catching that.
How about now?
Better.
You got it.
Okay.
Yeah.
Don, do you have my talk?
I couldn't find it. I remember seeing it come in the email, but who knows where it went. Oh, no, I'd find it. That's right. I'm thinking of the, our present. I did find it. Yeah.
You were running through them like that.
Yeah, I have. I found it.
Nice.
I'm thinking of our presenters bringing a USB drive.
Yeah,
So
that's fine.
we're good.
I like your sweatshirt.
Oh, yeah. Have that for years.
So, good? So you're gonna use your solar? Should I get now California? Helps. Well, the old days, house and it's long ago, but everybody's all that show. Yeah, that's it. But so it doesn't much to do with it. And trying to do it in the same size. Now, if you only little. Yeah. Exactly. Yeah. Now the other, you have to do the higher ionization, so the higher temperature. No, it's a wonderful. It's a different way of connection. The challenge in this book, the late Hadler, silly, and I think that's the best stuff. 10,000 Kelvin. And it's up to you know, yes, you can see what and sure, it's really she puts it in a range. Yeah, the version, right? Go when you're on the see, when those are all locked, you know. We go in the middle of the night, you know, doing this TV light. That's what you doors in behind. That's true. Yeah, so, learn about it's like true. Which constantly, someone's got true Americans, England, styles, because of your use of time. No, after all, where that male. He having, see, I think it's only right here. I threatened to say, honest, sure, yes, structure that fits on. So, you know, so that's, yeah. We need the bulk numbers. It's kind of curious. I mean, what's the difference in trading is that you notice it looks happy or when it's by the accidents. Like, it's good and stuff. But it's coding work, well, and the hot stuff will be, just separate out. It's really the mostly it's going to I come to learn Sequoia. Yes, that's actually. And yes, then what we do is they'll pay all that. For now, which was for the same. Yeah. That's again, that's like go to this is the flight rules. But 20 they'll pop up and run out of the flight street. Good, it's, you know, it's the old violent, you know? Yeah, and then they become kind of,
Yeah.
yeah, right, that's talking down, you know, my audience, you know, I'll have that. You know, at that point, as sort of, you know, introduce to your things, listen, see that, so, you know, you can like, both my research we've done it's an extra. What I do is I the irons is part of one, what's or like the all the articles, and then just guidance system too. The transition, see, this is what's and like. That's how I, you know, you shot sort of shit, so you get the answer to these. Was which way each other thought about. You can't remember you've done this sort of place. Yeah. When I started to write each little. So, that reading that. I will do a PDF. So it's kind of boring now because we're going down to 4 hours and we're going days. But this is also it's like their machines, you know, why they're thinking about type of activity takes instead of because you so you come in here to go in. Oh, speeding. I mean, it's not warm something, it's a wow. Yeah. Yeah, there's you know, some ones that kind of shifts the ground. Which is a lot of predictor. Please don't. And North Korea, not go back. It's a little better. But when you look at the magnetic there, there's still all 25 seconds and so I counted the membership that we can wait in, say 60 probably. How many students before we saw some maintenance? I mean, so it's hard to lay this time. They're still predicting deal with the skin. 2032 is be the ending. How they don't see some students they're thinking. Yeah. He's fine. Oh, we finally got really the fourth next time. You know, they was well in the before we got it's you know, I just well, then the other quick well. I'm not keep was in fact, I guess it was in the meeting. It's because it's just That's everything. That's where you're going. The squirrel. This I put in organic matter, but I suspect the gestures were still hands to set the. So I think it back to myself. Still, you know, just says. I should not get that thing pieces. I only pull back out to stick the. Yeah, that's right. And so, you know, we'll get some gas on there. Yeah, that's true. Yeah, no, I don't want to just willy-nilly put people name, you know, I don't know, standard. Because of. Why you have to cover your head, so regional for develop, so that if you could have. Oh, yeah. Yeah. Our schedule also have. Yeah. Usually we have. No, really, it's a suicide occurred at home. Because I started. I think that's like something, I don't care. One of those is which one will I got a drawing here, so. I'm wondering, how much have I did that's the door. I like day off. But it's no, always like that's all I said, six children. The rest, but all bringing for each of that. Please. I think we get thoughtful for something you got. Cool. Stuff. We're okay, that's just yes. He's got time. It's just. And yeah, and well, it's really hard to go. Is the law. It's only people that often yeah. Well, she wanted. Which I can see when it's. Good life, don't know. See her, it's been. Further, that's terrible, right? He has the burger. So I'm Hawaii. I'm shining. I like this situation. I'm almost wondering whether or not I'm with you. Then I think that's I'm trying to do something. Gain her those wants to move. It's really hard, so why are you about? You know, I see the few blocks. I've had them in my so but they asked like a question ever sent about, and you're like, sorry, you have to. You know, yeah, because they will monopolize the whole thing. We don't want to take it home. It's all about that. So Don, you're begging people to take food. Just want to. It's please take food. You should have caught. Once we have some stuff, we go this. Yeah, but just don't actually. Yeah. That's all they can ever ask that some junior can have those you are doing that. He's still on the screen, not calling. Yeah, it's what I'm saying, right? You want them to call. No, I show up. She's coming tomorrow. It's lunch tomorrow. Yeah, just with like Dan from DBA, talk about joint potential outage or outage. What time are you said you want to? Just give how much about. And they have an observing purpose. January, make sure how they. How you met. I'll talk with that Brett. You know where it is. He understands. I said understand what it's. Yeah. Word. I want to show them again. I'll try to hear that.
That's great.
Yeah, I'll do something out.
That was.
But yeah, one of us just go and challenge. How we collaborate, who we collaborate. Yeah. What can we do together? Especially like if we start doing more sidewalk. Okay, so. Just start farm. So yeah, good. So you ask the question, what are the nation of the sidewalk? See many eight scale. Well, yeah, it's just stick to shot. Right. That way. I would assume where they observe. That'd be great for them. This is tomorrow that we guys coordinate. Let's start this on something.
Who's Blake?
Yeah, I saw that. Someone's.
Whose butt was that?
We had an extreme close up.
What's that room thing? You know, that's not a working thing. And it's the front. And play for it. You don't keep I mean, that's oh, yeah, I'll let you.
Well, I guess that's what happens when you don't attend in person.
And so it, yeah. Yes, because that time, the vice president has spoken. Has to be true. We have not. Ready to rock?
Yep.
Okay. Everybody, welcome to Chester County Astronomical Society 2026. It's great to see all everybody. It's great in the cold and the wind to come out here, and it's gratifying to start off the year. We're going to have a busy meeting tonight, so I'm just going to cut to the chase. We have a lot to go over, and we have a lot to give out. So we're going to dispense with our usual "What's up" for the month because it's cold anyway, and most of us aren't out looking at IVs, except us crazy. Yeah, and we'll get down to business. First of all, I'd like to let everybody know that we have already a busy schedule coming up for the year in terms of observing events. So the first person I'd like to bring up is our observing chair, Don. Okay. And let's get right into it. All right.
Can we bring your slides up?
Please.
Okay, let me,
You know, we have a good sized club. We have, approximately 170, 180 members in the club. We all join for different reasons. This club brings in excellent scientific talk. Some people really enjoy the scientific talk. Other people like the camaraderie of other people who like astronomy. Other people really like going out and using their telescope. Sometimes in their own backyard, other times with giving it out to other people. And so I'm working on our 26 observing plan. So I just want to start with the next slide, please. If you look at our mission statement, if you go to our website and look at our mission statement, Chester County Astronomical Society is formed as a nonprofit organization dedicated to the education and enjoyment of astronomy for the general public. Okay, so next. That working there. So outreach is key to our organization. It's not just something a few of us do. It's really a core part of what Chester County Astronomical Society is all about. Okay, and so when you look at our membership, and I'll go over this again at the end, but really only a handful of us really tend to go out and do the outreach. And I'm working at putting up a lot of different events for us for the year. But it's like I'm selling things I don't own because I can't do it without your help. Okay, so I need people to come and help with these events. Now, don't take this the wrong way. You don't have to have a telescope or even a pair of binoculars in order to be able to help with these events. We just need you there. Believe it or not, as long as we have 4 or 5 telescopes, usually, except for a rare exception, right, we have a huge crowd. Longwood Gardens comes to mind, where we need more. What we really need are people just to meet and greet, man the tables, talk about, hand out literature for Chester County Astronomical Society, and help the flow of traffic, especially at the busy events. So each of the clubs in the area have kind of a different feel to them. Chesmont, they're all equipment geeks. DBAA is a little bit of everything. DAS is truly everything, and everybody's off in their own little corner. Whatever they want. The astrophotographers are separate. The scope restorers are separate, and they don't talk to each other a whole lot. But this club, in particular, our hallmark is that. So if we really need you out there, even if you don't have a scope, we could use you. I mean, an example is I'm setting up my scope. People always arrive before it gets dark. And so they're looking around to try, so Bruce is setting up scope, and I'm over there as a guest starting after about what's going on tonight. Meanwhile, he's trying to set up his scope. If we had other people there, trying to just say, hey, thanks for coming. Here's things we're gonna look at tonight. Here's some interesting stories about those things. You know, I, as the observer chair, will always try to put out information about what's gonna be seen tonight, so you can actually know that material. You're not alone in doing this. It's not like you have to come out and say, I don't know what's gonna be looking at this guy. You'll know, okay? And if you have questions, you have people like Dave, myself, Bruce, who can help you with that, okay? Next slide, please. So overall, nighttime, we have club events. I have a whole series of them at the RCA. And we have club camping trips to Cherry Springs that Dawn's going to be helping to organize. Opportunities to attend Star Park, as well as joint events. DVAA, our sister organization. And actually, we're meeting with them tomorrow to discuss more opportunities. Outreach events, we have, sidewalk astronomy that we're going to be doing. And so we're going to be setting up, hopefully in Westchester again, in the process of setting that up. Sidewalk astronomy, if you haven't done it, is a blast, and you just get people who are just walking by and they've never looked through a telescope before. And it's like an amazing thing for them to look through and see Saturn or the moons around Jupiter and say, what? And they're like thinking you painted it on them. I mean, the thrill you get just from them looking through is amazing. Okay.
And again, it's really about the observing zones, because how much can you see in downtown Westchester during the day, in the early evening? The light pollution is bad, but the few things that you can see, the public loves. And just having friendly faces there from the clubs means everything to people that are coming up.
And just explaining to people, it's one of the things, I call them barkers, but somebody now be talking to people who are walking by, hey, we're just County Astronomical Society, we've got a telescope here, like, come over. A lot of people just walk by and they're in a line like this, And so you want to basically engage the folks. And it's helpful for people who are on the telescope, someone else is engaging. So we have people doing that, it's helpful, especially for the solar events. That's all about sidewalk astronomy, essentially. And talking about that, so events at parks and schools, I'll finish that off for nighttime. But solar, Roger and team, as and his wife, really have an amazing system they set up. And some of us help out every so often, but a lot of those, like we set up on the Chester Valley Creek, right in the middle of the day. You get a lot of people come by. Some people could run right over it, okay? But other people, if you tell them, hey, I'm Chester County Astronomical Society, we're here with the sun. You want to look? And they're like, what? You can look at the sun? And so then, you give them some incentive to actually do it. So we need people. As Dave said, you don't have to have equipment. Just coming out and helping us in various ways is imperatively to getting these programs to work.
A friendly and inviting face is more than half the astronomy outreach. I'm telling you, that makes all the difference between a good event and a social event. So
Exactly.
come on out.
All right, next slide, please. Far as nighttime, we have 9 club events at the RCA. Okay, so starting in March will be the first.
We don't need help with that. That's just for us.
Yes, that's us. I mean, sometimes we have people coming, but
Rarely we'll have Girl Scouts and Boy Scouts come for their badges and that sort of stuff. That's a really rare event.
Right.
That's just a moment.
right. The camping trips, as I mentioned, Cherry Springs. It's supposed to be amazing. I haven't seen Cherry Springs yet either, so I'm remiss.
It's amazing.
I got to get there.
It is.
Public outreach. Right now, we have 12 nights planned, but I know I'm working on 3 others that are going to be there soon. So that's about 15, and we're likely to get more. I always get, as the year goes on, a lot of requests for us to do observing events.
Usually in the last month.
Correct. One thing we're going to do different this year is this university has a planetarium. So I've talked to the director of the planetarium, and what we're going to do is we're going to set up outside the planetarium. And when the show's done, goes from like 7 to 8. They're going to be exiting out right into the parking lot where we'll set up the telescopes. So it could be a match made in heaven. This will be our first time trying it. We'll see how it works. Okay. Of course, at the International Observe the Moon Night, we're trying to collaborate with the student body here, the Astronomy Club in Westchester. And then we have Friday Night Lights with all the other clubs.
Yes.
Next slide. Outreach events for solar. Just a few, 54 so far, as I count. Roger, you probably added more today.
54 events.
It's an amazing number. So, Roger can use help anytime you do it, because he's got at least 2 scopes, maybe gonna be doing 3 scopes, plus tables of information. And he's trying to go back and forth between the scopes and the table. A lot of people look at these tables, they don't understand what they're looking at. Again, you don't have to have a scope, just go do it. Museums. Okay, next slide. Next thing, we need you. So, I hope you're taking this to heart. I know you're all great. You love doing astronomy, but we really need your help. Next slide. So, bring your enthusiasm, no gear. If you have gear, bring the gear. Okay. If you don't know how to use the gear, still bring the gear. We'll help you learn how to use the gear. Okay.
And even if it's just binoculars, believe it or not, any good astronomer worth their salt, they always have a pair of binoculars tucked in their bag somewhere. That's always especially good for the kids and for the people that are a little shy around equipment. If you have it, bring it.
Yeah. I mean, I love just laying out at night with a pair of binoculars. I mean, it's just a fantastic view. So next slide, please. So I'll be distributing to the club distribution list a list of all these things in the next week or so, of all the ones I've got planned so far. I don't know about the solar ones, Roger, if you want to include those or not. But I'm asking you to look at the events, the dates of the events, and sign up. I'm looking at see who can I depend on to actually be there, either with or without gear. If you're coming with gear, tell me what gear you got, so I know what we've got going on. But basically, I want to know, do I have a commitment from the club to make it so I can run these events? If I can't run the event, then I'll cancel the event. Okay. So I'm looking for your support. We can review where we stand next month. Once we have it. Any questions?
And let me also add that I think last year, less than half of the events we had scheduled for the nighttime events didn't happen because of weather, and that's just the nature of what we do. But even so, if you can give us the commitment, it'll help us reach people and show people the sky. And it's really that fun.
Solar. I don't have a solar tunnel. I have a piece of solar fill. I'm not sure how safe. Just like a solar sheet. Yeah, we wouldn't use that, but we have, definitely really good solar scopes. We got white light scopes, we got H alpha scopes, and we have soon a calcium scope. You can utilize them. So once you're there, we can show you how to use them. You're welcome to try to do that.
We have a solar scope that if you've never looked through it, I mean, that's everybody in this room that hasn't looked through Radiant Scope. You gotta look through this before you die. It means you're amazing. But again, especially for the solar, the equipment isn't the issue. We have another solar scope, a small one, but I bring that to events. Even if you don't have the gear, if I know you're coming, I'll bring mine, set it up, and you hit literally, it tracks. All you have to do is show people in the eyepiece, maybe help along and let them enjoy the view.
When you see the prominences coming off the surface in Roger's scope, it's just breathtaking, and they're changed. You can actually watch them change. And so it's just amazing. And then you couple that with the white light, with granulation, as well as with the sunspots. It's fantastic. We're past the solar maximum, but still relatively close to that. So we should still have good activity for this year. Roger, agree?
Yeah, the forecast is, we'll start slowly going down, but we'll still have some pretty good activity. I mean, the Carrington event happened after solar max.
Right.
So there's still a lot of activity going on. We won't get a complete end until 2030 or 2032, but there's activity to see.
But sure, don't worry about gear. We have it. What we need is you. So anyway.
All right. Thank you all.
Thank you, Don.
Appreciate it for you.
And we look forward to seeing as many of you out there as we can. Simply and chilly because it's a heck of a lot of fun. And now to sort of change gears a little bit.
Awards.
Huh?
Awards.
Awards?
Huh?
Awards?
Award now? Okay. Okay, Don. We have some stuff to give out to those who involve.
Well, there's a couple things first.
Oh,
Okay, just want to mention that we are again offering
that's
Chester County Lifelong Learning, our astronomy classes. Normally they're like $60, but they're free to any member. So the important thing is you do not register. And I'll send this out in an email. Do not register, otherwise you got to pay. You send this will be in an email. You send it to education, which comes to me and Dennis O'Leary. Well, they're going to be 6 Wednesdays from March 18th to 22nd at Pierce Middle School. So there's 6 classes all taught by us, and they're pretty good. So they are free to members. I just wanted to point this out. Don Miller was interviewed by a lady that writes this Westchester Neighbors magazine. And did you send this to everyone or not everyone?
I thought I sent it out to everybody.
Okay, it's a great article. So yeah, I know you sent it to us. I don't know if you sent it to the whole club.
I'll take a look. If I haven't,
Okay.
I'll send it out.
And we're sending out at least just that one page.
Yeah.
We're sending out. So it's a great article all about us. And then our annual giving out of the awards for NASA Night Sky Network. Beautiful pins this year. A lunar eclipse with an adult and a child in a telescope. So these are really beautiful,
Wow.
beautiful pins this year. So if your name is up there, we have a pin for you and a certificate. So please come up.
So please, Sue Johnson, Bruce, Don
So
Miller.
why don't we hand them out as we go,
Okay.
and then come to me to get your pin.
Thank you.
Sue, I'll take yours first.
Thank you. We got your pin earlier.
Yes, and Roger. Oh, you got your pin already.
But here's one for Linda.
I didn't get one for Linda.
Yeah.
Pete?
Pete Kellerman.
Here's Pete. Here's the pin for you.
Who's that? Thank you. Pete?
Jones. I never heard of him. Steve?
Thank you. I need one for Ann Miller.
Yep, and big one for Randy.
Yes.
And that. And is that everyone?
No, yours here. Steve Harmer.
He just got his. And I'll let the listener do later and pretty soon it shows up later too, so. We'll get to that too, okay?
So anyway, for all our Night Sky Network folks that got their pin there, thank you so much for coming out and helping our club keep to its mission in terms of public outreach and showing general folks out there that, yeah, astronomy is not just something that's done by space telescopes on the internet anymore. It's still out there, the sky's still out there.
Just because it shows up.
So, thanks again. Okay.
All right, so I'm going to load up our presenters. You can introduce while I do the,
Yes, we have one more thing to announce.
Okay.
If I could, well, you go first. Oh, no. Okay. So I think everybody knows that I'm Bruce Gary, program chair for the club and also the Westchester scholarship coordinator. That we, some of you are familiar with. Just 2 brief announcements. The first is we have our scheduled speakers, including tonight,
Okay, but-
out through May. We have some really good people coming, some in person, some are from NASA, JPL, a few people coming from Ames, we have someone coming from the Carnegie Institution in Washington. There's a good diverse lineup of speakers. However, intentionally, I've only booked until May. We have a hiatus in the summer and then we resume in September. So I always put this out at the beginning of the year. If you have any topics that you are really interested in hearing about, I try to choose a very diverse range to appeal to a broad range of interests, very astrophysical, cosmological, planetary science. If there's anything you're interested in, reach out to me. My email's in the observations, all our correspondences. Let me know. If a person is around, I will find him or her. And the beauty of Zoom is you don't even need to be at the same time. So let me know and I can try to schedule them for the fall because I do want our talks to appeal to the majority of the audience. The second point is, if you are a member, you should have received from me probably last night a mailing about our scholarship fund. Just to recap very briefly, we have this fund that this is now 4th year, where through your donations, not club dues,
your donations, we've been able to give three $1,500 scholarship awards to students at Westchester who are either STEM majors or working in physics, astronomy, earth science, computer science, but they have clear aspirations for careers in astronomy, planetary science, or space-related field. It's been enormously successful. As Don pointed out, outreach is core for what we do, but so is education. And this is sort of part of our core education mandate. And so I have to come to you every year and beg for money. And the information is all in the email. I won't go through that, but I just really ask for your continued support of generosity. This does make a difference to students, and it does serve as an inspiration to those students to want to continue in these careers and pursue professions in astronomy, space, or planetary science. So I do ask for your support. Our goal this year, given what we already have in our fund, it is about $3,500, and we've always made our mark every year for the past 3 years. So I'm hoping this year will be no exception. We're also talking about, look to the future, about creating an endowment instead of the scholarship fund. Dave and I had met with the foundation here at Westchester, and I won't get into the money parts of it, but let's just say we need to raise a chunk of change. But if we do that, establish an endowment within a few years, as the return from that investment comes in, we will be able to offer these scholarships in perpetuity, and we won't have to give funds, right? Even long before, when we're all stardust again, the scholarships will continue on, and any monies we do raise will only bolster the endowment, so that if we wanted to offer more scholarships, or we wanted to increase the amount for a given scholarship to worthy students, we can do so. So this is something David and I are working on. It's the process because there's a lot of dollars involved. But again, it's always looking to the future, that not just outlays, that education is really important in this organization. And the scholarship fund is a way of supporting that. Also, we have no say in who gets these awards. A committee in the Earth and Space Science Department, they review all the applicants, they choose them on the basis of merit, and to some extent need and interest. They tell us, and then I take care of the paperwork and move the money around, and the foundation administers the award to the recipient students. So just putting out a call for it, please be as generous as you can.
Yeah, I mean, we've always had a special relationship with Westchester University from the very founding of the club. And this is something it's important for us, but it's also important for these students as well. So please, thank you for the support that everybody is giving. And thanks again, prospectively, for the charity and the good support that you've given us in terms of supporting the scholarships in the future. This has to continue, and we're going to try and make it so that it's almost automated. So thanks, Chris.
Okay, so to introduce our chief, several years ago in the Chemical Magazine and in Nature Astronomy, it was pointed out that neutrino astronomy was one of the hottest emerging areas in the field. And we are really, really fortunate where we live in that we have one of the leading experts in the world, I think that's fair to say, in this field right in our own backyard. And she is tonight's speaker. So Dr. Naoko Terahashi is a astrophysicist and neutrino astronomer at Drexel University. She did her undergraduate work at Berkeley, her PhD at Stanford, and then postdoctoral work in Wisconsin. She's been at Drexel for 12 years, and she's now a professor of physics. And her work, essentially, it revolves around studying high-energy neutrinos, the sources of those neutrinos, and more sophisticated ways of detecting them. And she and her group actually did some in that they published the first neutrino map of the Milky Way galaxy. So it's a real honor to introduce Dr. Naoko Terahashi.
Thank you so much. Hey, hi, Chester County Astronomical Society. Let me see if I could. Maybe screen three. Is that better? Yeah. Okay. So my name is Naoko, and that was a very generous introduction. That is me. at the geographic South Pole, and I'll explain why I'm there and what this has to do with astronomy and all that. But let me just tell you where the geographic, so there's no mic, right? I can move around. I'm very animated when I talk. So let me, what this is, right? So if you take a compass and you look for which way it points south, you follow that, you go to the magnetic South Pole. So this is not the magnetic South Pole. This is the geographic South Pole. So if you think of a globe, and usually when I go do this talk at like elementary schools, I bring a globe because you'd be surprised how many kids haven't seen globes. They've seen a map, but it's not a globe. So you bring a globe and there's two sticks and then the earth rotates around those sticks. So the bottom stick where that stick intersects with the earth, that's right there. So around this point, well, we kind of stick the stick it's all the way around. But so the skies revolve around this point. So, it's a little trippy because what does the sun do at the South Pole, right? So every day, let's say you wake up and the sun is there, then in 24 hours, the sun does this. Well, I was there in the summer, so that means the sun never sets, right? And then every single day, the sun gets a little bit lower, right? And does one revolution around the sky, a little bit lower. And then you have a couple weeks of sunset where the sun hugs the horizon all the way around, and it gets lower and lower every day. And then it finally sets, and you have 6 months of darkness. So that's what it's like, right? Other interesting things about the South Pole, when you stand there, every single direction you can face is north. Right? You think about that, right? You're like, what time zone are you in? You think about time zones. A lot, yes, all of them. So all of the conventions you are so used to, not at the pole. What the sun does, how time moves, what should happen, which direction is north, all of that you have to rethink, which is kind of incredible, right? Like it's very refreshing and disorienting at the same time. So that's the geographic South Pole. Later, but it's actually quite high altitude. So when you stand at the geographic South Pole, you're standing on about 3 kilometers or 2 miles of ice. So there's a huge glacier underneath me, which is important for what I'm going to talk about. Since it's so high, so that's what, like, I want to say like 30,000 feet? No, 3,000 feet? No, wait. Oh, don't let me do unit conversions on the spot. 3 kilometers is 9,000, right? Am I right?
Yeah.
Yeah, okay. So it's quite high altitude, especially if you're from the East Coast, that's high altitude. I'm from the West Coast, so it's all right by me. But I actually did get altitude sickness, and I had to take pills for it for a while. So it's really interesting. I'll get to more interesting things about getting to the South Pole later, and the altitude and all that stuff. Okay. So I'm gonna start with a disclaimer. I'm not an astronomer like you. I am an astroparticle physicist, and I'll explain what that means. So by training, I'm a particle physicist. So particle physicists, we study small things in the universe that you can't see. So fundamental particles. What do I mean by that? Elementary particles or fundamental particles are things that you cannot break apart, right? So you, me, the air, the desk, everything is made up of molecules. They're made up of atoms. Atoms have electrons in the nucleus. Electrons, as far as we know, are not made up of anything. You smash electrons at high energies, right? So now high energy physics is what I'm describing here. This is my training. You smash electrons at high energies, it does not break apart anymore. So as far as we know, electrons are fundamental particles or elementary particles, right? The nucleus is made up of neutrons and protons are made up of quarks. And as far as we know, quarks are not made up of anything. So these are fundamental particles. That means even in the highest energy parts of the universe, violent black holes, whatever, where there's so much energy for these things to collide with each other, they do not break apart anymore. They are fundamental to the building block of the universe. So that's my background is I'm a high energy particle physicist. Okay. But I look at maps of the universe and make maps of the universe. So I'll tell you why in a second. And just to get street cred with you guys, I do work with people at NASA. So, you know, I give talks there, but I also do a lot of community work at Goddard. I'm down at Goddard, like, I don't know, a couple times a year at least. So I'm not an astronomer like you, but I'm an astroparticle physicist. And today I want to tell you about what that means, and I think the new frontiers of astronomy, if you will, that where the boundaries of astronomy and particle physics meet, what we're creating and what kind of knowledge we're gaining. Okay, so here is what I'm going to answer for you. Why particle physics? Why the South Pole? And actually, do you do astronomy? Okay. So let's do particle physics first, right? So this experiment I really like. So let's pretend like you guys are aliens, and you guys are alien scientists, right? You have an alien scientist PhD in the human hand. So your specialty is studying the human hand, right? Let's pretend like you have alien hands, you don't have human hands. And this is the only human hand that you have ever seen. And you need to study my hand. But the kicker is you have to study it from where you're sitting. You can't come and dissect me or touch me or anything. What would you do if you were a good alien scientist studying the human hand? Right? And the answer is you would look at my hand from there in different ways. So you would look at it optically. This is your astronomy, right? Like most of your telescopes, right? So you would look at it with your eyes, your alien eyes, I suppose. And you would see that it's, I don't know, my hand's like yellowish pinkish. I have like 5 ridges that are fingers, what have you. And then you would put on your infrared goggles, right? And you would realize that my hand was warm just from seeing my hand in infrared from where you're sitting. You would know my hand is warm. If you took an X-ray image from there, you would realize that I have bones inside my hands. And if you took an MRI image, which might be a little difficult from there, you would realize that I have muscles in my hand. And so the point is, by looking at my hand in different ways, you can understand what it is better if you can't come and dissect my hand or touch my hand. And the same thing happens for stars. So this is the Crab Nebula, which is, if you don't know, you probably know better than me because I'm not an astronomer once again. It's a star with a lot of stars. That's how I imagine. And this is looking at the same star in different ways, right? And you notice, even though it's the same thing, you pick up different things about the star. And when you combine everything, even though we can't get to a nearby star, there's no way we can like fly probes or anything. If you can look at it in different ways, you learn more about that thing than looking at it in one way. So, of course, when I say things like radio, ultraviolet, optical, and X-ray, what I mean is this is different parts of the electromagnetic spectrum. So this is what I'm actually teaching right now. I'm teaching EM waves in University 201, or no, Physics 201, but this is all part of light, right? It's just optical light, whether it's high energy and high short wavelength, high frequency, or low energy, low frequency, high wavelength. These are all different types of light, right? What I want to do is to see the universe in particles. So I talked about fundamental particles because I'm a particle physicist. I know that just like light, there are many particles that stars and black holes create. And if we can catch those on Earth, just like we catch photons, just like we catch light, and we put it together, we will understand more about things we can't get to. And that's my goal. So this is the boundary of particle physics and astronomy. Okay. So specifically, the particle I'm interested in is in neutrinos. And you go back to this and you're like, yeah, but like you told me what things are made out of, but you never said neutrino. And this is correct. So neutrinos are not something that make up me, you, Earth, desk, whatever, right? So it's not part of what makes us us. But they are particles. They get created mostly when the nucleus breaks. So these are like fusion, fission. Oftentimes you think about neutrinos from radioactive sources. You think about neutrinos from nuclear power plants. You think about neutrinos from the sun, actually. The solar neutrinos is a hot topic, maybe, I want to say 3 decades ago at this point. So when the nucleus breaks, in the breaking process, it makes different kinds of particles, not just the constituent particles that are quarks, but It breaks and blah, a lot of things come out. And some of that is neutrinos. And the good thing about neutrinos, or the bad thing, if whichever way you want to think of it, is that they don't interact. They rarely interact, right? So what does that mean? Why is that good, right? So let's say, I have a flashlight, right? And I'm trying to shine my flashlight through this desk to you. You won't see light coming out of this side, right? And that's because the light from the flashlight interacts with this desk and it doesn't make it through. That's why light has the fancy word astronomers use is optical depth. It has a shallow optical depth. It has a small optical depth. It can only penetrate so much, right? So then you won't see it. If I had a neutrino flashlight, which nobody has, but I wish I had, if I had a flashlight that just gives off neutrinos and flash it, you would see neutrinos coming out of here. So what is this an analogy of? This is an analogy of if there is a star or a galaxy that's obscured by things like dust, and we can't quite get the whole picture using light. Neutrinos are a great way to look at it because they don't interact with matter. They don't interact with the disk. They don't interact with the dust around the star, the galaxy, what have you. Okay. The other good thing, so that's what I mean by rarely interact. Another good thing is that they are not electromagnetically charged. So if you remember if you've taken this already, electrons are charged, right? So if you come across a magnetic field, right? If you have a magnet, electrons bend. So what does that mean? That means that, let's say I want to be an electron astronomer, right? Neutrinos are too hard. Sounds exotic. I know what electrons are. Let me study electrons from stars. Well, there's a couple problems. There's no optical depth, but even if there was, because there's a lot of intergalactic magnetic fields, the electrons bend. So you see an electron coming from that way, it might have come from a star over here, right? Because it bends in coming to me and it comes in like this, right? It does a curve. So if the arrival direction is this way, I don't know which way the star was, right? So you can't do astronomy with things that bend, things that don't trace where they came from, right? Light is electromagnetically neutral. That's why you can trace back. If a photon hits your eyeball, right? You know it came from there. That's how you can see stars with your eyes. So this is a good particle, we think, to do astronomy because it doesn't interact. It has it can go through stuff and it doesn't bend. Okay, so that's why I think particle physics might be important for astronomy. Why the south? All right, here's a second thought experiment. So when I do this talk in the Midwest, it goes over better, this part. So I don't know if you guys have ever had the privilege of going to a snowbank and sticking your head in the snowbank. But if you do, you would know that it gets dark pretty quickly if you stick your head in snow. Now, if you bury yourself in 1 mile of snow, do you see any light from the surface? No, it's pitch black. It is pitch black until you see a high energy particle whiz through, and they emit what's called Cherenkov radiation or Cherenkov light. So every high energy particle that goes close to the speed of light, so we're talking relativity here, right? So we're talking relativistic speeds. So if you have a high energy particle that goes through something, it will usually emit what's known as Cherenkov radiation. And this is like this bluish hue of light. And if you can see that, you can tell which way that high energy particle came from. So, excuse me. So what we did was, remember that picture on the first slide where I'm standing up high, where I did shady unit conversions? Yeah. So 2.5 kilometers high, right? So we buried light sensors, the bottom of this glacier where it's pitch black. And every time there is a high energy particle that goes through, it emits these Cherenkov radiation, this blue light. And these light sensors will detect them. And this is how we catch high energy particles. Let me just explain this a little bit, right? So let's see, there's just so much to talk about. I don't know what to talk about first, usually. Maybe, what do I mean by light sensors? So, I don't have a better picture. Ooh, I usually have a better picture. I'm sorry. Okay. It basically looks like a humongous light bulb. It looks like a light bulb that's about yay big. They're called PMTs, photomultiplier tubes. And every particle physics experiment uses this to some extent. And what they do is they look like a light bulb, but they actually do the opposite. They catch light. So even the faintest light they can see. So we're trying to catch this Cherenkov radiation coming off of high energy particles. If you've ever seen like nuclear waste pools, and it has like this eerie glow of blue, or sometimes in movies, it's depicted as green sometimes, because I guess they confuse it with toxic chemicals. I don't really know. I'm thinking of like The Rock and the Alcatraz. What's that movie with Nicolas Cage? You know what I'm talking about? Yeah. Anyway, it doesn't matter. I'm old. Um, but so you get this like eerie blue glow in nuclear waste pools, and that's because the spent fuel rod, right, it's not done yet, and it still is emitting high energy particles through nuclear processes. And because you don't want that to heat up, you dunk it in the water, right? You don't want, I mean, I don't know how many of you are understand nuclear physics, but you don't want neutron avalanches, so you moderate it in the pool, in the water. But so the blue glow comes from Cherenkov radiation. That is high energy particles almost at the speed of light, emitting blue light. So this is the same thing we're catching, except we're catching it one by one. And we have a humongous detector. So this is called Ice Cube. It's called Ice Cube because it's a cubic kilometer height. So essentially we've got 5,000 of these light catchers. We put it down in where am I? We put it down in these really deep holes. They're on string, and again, it's pitch black in there, and we are catching extremely high energy particles that could only come from black holes and other violent processes of the universe, right? So nothing Earth made can really give off light that kind of traverses a kilometer scale detector. That's why we need big amount of material. That's why we're helpful. So we have these light sensors on a string, and what we do is we have drilled down. Actually, there's no technology that existed to drill down 125 meters of glacier ice. So we had to invent that. They say we drilled down, sorry, not 125 meters, 2.5 kilometers of glacier ice. So I say like very nonchalantly, like, "Whoa, we figured out how to drill 2.5 kilometers of ice straight down." But you tell me to run 2.5 kilometers that way, I cannot. Like, I'm so out of shape. Now you take that distance and you think about drilling down in an ice sheet, right? And your holes can't go wonky. It has to be straight. I mean, it's kind of an engineering nightmare if you think about it. But they figured out how to do it. And so the holes are about yay big, just shoulder width. If you fall, you fall. Right? That's the joke.
That's a lot.
It refreezes obviously because the outside, ice is clearly cold. So what we do is we shoot hot water down and we melt gradually, and then it's a race against time because like it fills with water, the melted thing, right, with ice, and then it refreezes, and then you have to like put down your light sensors as quick as you can, make sure the readout works, everything. And you do this 86 times. You drill 2.5 kilometers deep.
How do you choose the separation?
Yeah, this is a great question. I actually love questions while I'm on topic on the talk, so please feel free to interrupt me. So actually, the separation of the light sensors gives you a scale of what energy you're interested in. So rule of thumb is further apart these are, the higher energy you're interested in. So if you've ever heard of like Super K or like all these like mountain mine neutrino experiments, Sudbury Snow Lab in Canada. These are like in mines. They have smaller but still big neutrino detectors, and they have PMTs really close together. Those are much lower energy neutrinos they're trying to catch compared to us. So because our PMTs, our light sensors, are 125 meters apart this way, and 125 meters apart this way. sorry, I'm getting my measurements wrong today, and 17 meters apart this way on the same string. That's quite a large spacing in the particle physics community. And that large spacing tells you that we're not interested in, some ordinary high energy particle. We're interested in the highest energy particles in the universe, so high energy that we know we can't take it on. So that's why the size becomes so humongous, right? We're instrumenting is the word I like to use. I know people don't like it, but we're instrumenting a cubic kilometer of ice to be our particle detector, essentially. Yeah.
Do you have to be concerned about geologic instability that, when you think you put it somewhere, but
Yeah. So story.
yeah, thanks.
Story. So it turns out because Antarctica is a continent, unlike the North Pole, the South Pole is on a continent, the continent of Antarctica. And this might make sense kind of intuitively. The continent is warm, right? Like dirt is warm, right? So they think there's like a thin water layer between the continent and the ice sheet. So the overall effect of this is that the full ice sheet is sliding down the continent. So I told you that pole, right? There's a pole that was stuck on the ground. We have to, there's a ceremony every year where you re-stick it, you move the pole like 10 meters away and you re-stick it. And it's not because the point at which the Earth is moving around has changed, it's because everything is sliding down. The whole ice sheet is sliding down the continent. So the ice sheet moved. Isn't that insane? Yeah, it's not a trivial amount either. Yeah. It's kind of insane, yeah. South Pole, crazy. Yeah, go. Yeah, it's gonna get annoying in a second, I think. But all right. Of course I don't do this by myself. It's a full collaboration, it's a worldwide collaboration. I work with so many institutions around the world. And we're about maybe 400 scientists now. So Drexel's part of this, obviously, but it's a big. I'll talk more about the people in a second, but it's a wide effort. Okay, I'm gonna do an interlude, a show and tell of how to get to the South Pole. Because why not? Because even though it's an astronomy talk, the South Pole is so cool. Okay, so if you only see a map in 2D, Antarctica is like this long white thing on the bottom, but of course that is a projection issue. The continent is not a long white thing. Actually, I've about this a lot lately because of geopolitics, probably. It's very important for kids to look at globes and not just maps, right? I think because it's so hard to tell people what 3D things actually look like in 2D on a flat map. You know what I mean? Like, like Greenland can look so big on a projection. You know what so anyway, okay. I messed up. But it's so you like I have never seen on a map what the continent of Antarctica looks like until I joined this project. It's the first time I actually took a globe, looked at it upside down, and said, "Oh, this continent looks like," and it looks like this. I had so this is not just others, me too, right? We don't have a good sense of the 3D world because we always see it in a 2D flat map. But this is what the continent of Antarctica looks like. So this is, that's the South Pole. In order to go to the South Pole as scientists sponsored by the US government, you fly to New Zealand, Christchurch, New Zealand first. You go out of the usual Christchurch Airport terminal and you go to the next building over, and this is called the USAC Passenger Terminal or United States Antarctic Program Passenger Terminal. You go there, you register. This is how you fly out to any part of Antarctica, actually. USAC also gives you like full gear, so you'll see in subsequent pictures we all look the same. It's because we all get issued the same gear. It's really good gear, actually. It's really good gear. You have to return everything on the way out. So yeah, I know, but they really give you like socks, long john underwear, like everything, gloves, many layers of gloves, many layers of everything, boots, many boots. So it's their responsibility to make sure you don't die there, even if you show up in like flip flops and pink top and so they give you enough gear. So it's funny. So these parties, the what we call big reds, they're they're made by Canada Goose. The company I think it's called Canada Goose. Canadian Goose, yeah. So like 10, 15 years ago, they used to become really popular amongst US college campuses. And this is the USAC badge. So our Canada Goose parka has this badge on, but the ones they sell commercially has a very similar but not quite the same patch. And I was seeing it all over campus. And I was like, what is people do that? It was like a fashion thing 10 years ago, 15 years ago. I don't understand it. Okay, anyway, that's a big I gotta keep an eye on my time. All right. Okay, so the continent of Antarctica has many stations, but run by many governments. Do you mind if I take a bottle of water?
Please.
Since we like very animated and very happy to talk. Thank you. Yes. So I'll let you stare at this map for a while. So if you're again a US person, you fly to McMurdo Station first from New Zealand. So New Zealand's this way, you fly here first. And then this is the largest base on the continent of Antarctica. And then you fly from here to the South Pole Station. I can tell you a little bit about the name of the South Pole Station. Anybody know about Amundsen and Scott? Yeah, they were in a race to reach the South Pole. This is about 100 years ago, 120 years ago, maybe now. Nobody had ever visited the South Pole. Everybody knew that 90 degrees south existed. It's very hard to get there without modern equipment. So, Amundsen was a Norwegian explorer. Falcon Scott was a British naval officer, and they were in the race to reach the South Pole, be the first to reach the South Pole. Actually, the staging for Scott's expedition is like so they used to go to this coast first, abandon their boat there, and then walk. And put people of food along the way.
What's that distance?
Oh, it's a 2.5 hour flight by a C-130 Hercules. That's the only thing I know how to say. But yeah, so long story short, Amundsen gets there first, leaves Scott a letter saying, haha, we got there, or something like that. Well, actually, it's actually a very heartfelt letter that says, if I die on the way home, please, say something like that. And then Scott sees this, gets there second, realizes he's second, devastated for country and king. And then they all die on their way back to their ship. It's really, you can read Falcon Scott's journals. It's something very accessible. And it's just, yeah, heart-wrenching stuff. This is also like very like for my country and my honor, right? Honor for my country, like it's very different from what you think about today. So it's an interesting read if you're interested in Antarctic history and things like that. Anyway, that's what the South Pole Station is named after. I was actually there at the South Pole Station on the centennial anniversary of Scott reaching at the station, not of Amundsen, but of Scott. And so we had like British Navy was there we did a little ceremony. It was really heartfelt, actually. And explorers, man. There's something about explorers that I think scientists and explorers, we all both like unknown things to be known. So it's like the age of exploration is amazing, right? Anyway, what was I going to tell you? I was going to tell you that I'm going to first fly to McMurdo from New Zealand. So this is me arriving at McMurdo Station. This is a very big station, like I said. The ice there is nice, and so they can clean the ice nice enough that ice becomes the runway. So there's no tarmac, right? There's the plane lands on wheels, and they have to clean the ice so that the plane can land, right? So the airfield called Pegasus, this is called Pegasus Airfield, is a little bit away from the station because you kind of want to be out in the sea where the ice is flat and stable. So you land out there, and then there's this Ivan the Terrorist that takes you to McMurdo Station. That's me inside this. This is a C-13 plane, I think, cargo plane, and that's me in the corner, away from the cargo. And then McMurdo Station is it's very nice. It's cold. There's penguins. It's coastal. It's big in terms of Antarctic stations. But then you fly to South Pole Station from there, and the plane gets much smaller. So again, this is the C-130. This plane takes off in wheels. I don't know if you can tell. There's wheels here, and then lands on skis. So at the South Pole Station, there is a skiway, not a runway. So the South Pole Station, they have to maintain the snow so that it's flat enough that you can land on skis. It's much smaller. Cargo plane, there's me. Behind this curtain is the bathroom. Around this corner is where the pilots are. These are the pilots flying the plane. He was reading, because you just fly over, I guess. So yeah, you fly over these beautiful Trans-Antarctic Mountains to get to the South Pole. It's amazing. And then, as I said, South Pole is this, it's flat, it's white, and there's nothing else, and it's a glacier, right? It's a flat glacier. So I was looking outside the window as this plane was descending, but I couldn't tell, right? So I was like, oh, I wonder how much longer until we land. It seems like we're fairly high up, and then we just rattled and landed, right? So you have no perspective. When it's just flat white and nothing else down there, you have no perspective how far off the ground you are, because it looks the same at cruising altitude and when you're about to land. And so these pilots are very good pilots. It was very impressive. Anyway, you land, here's the ski sound, right? So now you're not using the wheels, you're using the skis to land. Here's the South Pole Station.
You give the coats back when you're leaving?
I do. So on the way back to the US, when I pass through New Zealand, they make sure to get all the nice gear back, unfortunately. I might have kept a pair of socks and a pair of long underwear. Don't tell the government. So it's beautiful. So South Station, nothing like McMurdo, right? Nothing like anywhere I've ever been on Earth. It's flat, it's cold, it's white, it's dry, it's high altitude. Nothing lives there, like not even bacteria naturally lives there. It's too cold. Like there's no living thing at the South Pole unless we introduced it. Yeah, it's just so desolate and white. And in the Midwest, I always say that it's like Southern Illinois in the winter. That's a joke that goes over well. But yeah, it's like another planet, really. I don't know how to explain it. Yeah, I have a video on this USB stick, so if I have time later, I can show you some videos.
Meteorites that's around, like they say, they collect.
Around here, so infrastructure is not great. So the meteorite hunter, I know what you're talking about. The people who go and like collect meteors from years ago, I think they're out of McMurdo Station, and there's this flat valley called Dry Valley that's accessible by helicopter from McMurdo Station, and I think that's their favorite place to track these things. Yeah. I think it's just logistically much easier to be there. There's a quite a bit of snowdrift at South Pole Station because there's so much snow and it can get windy because it's the plane, right? Essentially, like there's nothing of steering, so it gets quite windy here, which means that there's a lot of snowdrift, so things get buried very easily. This is why if you look at this, the new station as of 20 years ago, new South Pole Station. So every building is on stilts, so that even when the snow comes, you don't get buried in. So everything here just gets buried. We are currently constructing more detector at the South Pole and things we left there last season. And I'll talk about seasons in a second. So a year later, you have to actually dig out from the snow because the snowdrift will entirely cover it. So it is, I went in the summer, Austral summer, right? So there's summer, our winter. So right now there's summer, it's summer season, so there's a lot of activity. And planes can, as long as the conditions are good, planes can fly in and out every day. In the winter, it gets too cold for planes to land. So, maybe I have a, okay, I'll show you the video later. Yeah. Yeah, this is called winter over. So, every year, volunteers, people who choose to do this, will spend a year at the South Pole, including 6 months where there's no planes coming in or out. So these are the brave 30-odd people who will spend the entire winter at South Pole Station. That's the last plane leaving that year. They will not see another person for about 5.5 months. And then soon the sun sets and there will be no sunlight either.
What do I?
And they're stuck in there for the whole winter. Those of you that remember the movie The Thing from the 80s, you know what I'm talking about. So apparently the winter over is when they say goodbye to the last plane of the season. They all go to the movie room and watch The Thing. So that's the kind of thing.
Could you catch a cold there?
Yeah, you
You
can
said there's
actually.
no bacteria.
Yeah. So actually, really easily, the same way you can catch a cold really easily at school, which is that you bring bacteria from other places, right? Or viruses, and then you live in close quarters and you don't go outside much because it's cold, just like it is now. And you have recess and never, you play and you learn in a confined area. What you do is the virus really circulates around well. So once somebody is sick at the South Pole, everybody gets sick at the South Pole. Yeah. Yeah.
So you said there's about 400 scientists in your group.
Yeah.
At this station, everybody
Yeah.
supports that. How many people at any one time are living, working year round?
Yeah. So in the winter, 30-ish.
Okay.
In the summer, it depends on the activity, but I think they have like a capacity of 100 to 200, I want to say. So yeah, so it's a commitment to stay winter over at these places. But of course I went like a sane person in the summer. One more joke. So in order to winter over, you have to pass the psych exam. The joke is that they make sure you're already vanished. Okay. All right. I was talking about that long sunset. This is what that looks like. These are pictures I got from yeah, I'm sorry. The resolution of this projector is not fantastic, but maybe I can post slides later. It's beautiful. And then here's like that sun moving. So I think this is like I don't every half hour or something like that. This is how the sun moves. Anyway, okay, so that's the South Pole. Here's our like I said, our detector is buried underneath, our light sensors are buried under here, right? But all that cable and the data has to come up to the surface. So the cables come up here through here, and this is our computing center. So there's a lot of servers in there that process our data. We have lots of data coming through every day, every second. So that's our experiments computing warehouse. I like this picture because it has two things in the sky. One is Aurora Australis, Southern Lights. It's beautiful. One great thing about wintering over is that apparently you see auroras all the time. And then the other thing you see here is the Milky Way. And the Milky Way has been studied forever. It's such a prominent feature in the sky. It's the biggest thing you can see. So there's a lot of write-up in astronomy about the Milky Way, right? So what do I want to show you? Okay, I want to show you this image of the Milky Way. This is a really popular poster from NASA that I'm sure somewhere in this building there is a version of this. I don't know which year. But I want to explain to you what this poster is because everybody's seen it in astronomy. So we live in the Milky Way. It's a spiral galaxy. It looks like that. So it's spiral arms. The sun is like yay, right? So it's spirally and it has a lot of stuff, but it's flat. So what that means is like we live in like a flat circular thing, but it's a little bulge in the middle. So it's like a pancake essentially. So it's like a circular pancake, and we live in the sort of the rim of the pancake, if you will. So if you live inside the pancake and you look towards the center of the pancake, right, you see the cross-sectional view of the pancake. It's almost like when you slice the pancake in half. So that cross-sectional view of the pancake looking towards the galactic center, the Milky Way you see in the sky. So that is our galaxy as we see it from here, right? From inside, so inside the depth of this circular thing. Okay. So you straighten that out, you put the galactic center in the center. This is called the galactic coordinates. And what you're seeing here is our galaxy seen by different wavelengths of light. So remember that Crab Nebula, the human hand alien thought experiment? This is our galaxy seen in different wavelengths of light. So you can pick up similar features, different features. It goes from radio up top all the way to gamma rays down below. And what we did at Drexel with my group was for the first time ever, we added another panel to this, not in a different frequency of light, a different wavelength of light, but in neutrinos, in high energy neutrinos. This is the first time we see our own galaxy in anything other than light. And it's also the highest energy picture of our galaxy. And it's very blurry, it's not great. I will give you that much. But this is the first time we've ever mapped it.
Can you correlate sources to the different?
I mean, so that's exactly what when I give like seminars and colloquia at astronomy departments, this is the first thing, right? So we don't claim we can yet. Right next to our parents. We don't claim we can yet, but you can't help but look at it and go, huh, that dot's there, that dot's not. And if you give this talk at NASA Goddard, they're like, can you stay on this for a couple minutes? And this is, yeah, right. Astronomy is astronomy. It's human nature. This is exactly what you do, what I do when I look at the night sky, and this is what NASA astronomers want to do when I show them this picture. Yet to be seen what similar and different things mean here. Yet to be seen, yet to be found out. But anyway, we made this discovery. We had this press conference at Drexel. That's my graduate, former PhD student, Steve Sclafani, who did, this was his PhD work. Yeah, we had a big party afterwards. We did a lot of popular press. So I have been involved in a couple of discoveries now, and I have done a lot of popular press. And it's really interesting. Oh, I'm missing a slide. So the first popular press tour I did was about 10 years ago when we actually discovered neutrinos from space. But it's a different story that I didn't tell here. But it's really hard to explain what neutrinos from space being discovered is in one line, like one headline. And like, oh man, the science journalists, they struggle. You can tell, like, one article was like, and I think it was Fox News, was like, scientists at the South Pole discover outer space. They understand the struggle, man. Like, I wouldn't know what to write either. You can't say astronomical neutrinos observed for the first podcast, right? So this one was a little bit easier because it was about the Milky Way, and so there's a little bit of like this ghostly new portrait of the Milky Way. That's kind of a nice way to phrase it, right? So we did a lot of interviews. I particularly like this New York Times one. Like, I think the writer here was really good. So if you have New York Times access, like New York Times access, please have a look at this and read this. It's very readable. It tells you what we did. I even did a lot of popular press interviews in other countries. So this is CCAS, which is basically like what's it called? What's that science magazine that everybody reads in America? Scientific America. Yes. This is like the Scientific America of France, essentially. So I got a really sketchy email, and I was like, this doesn't seem real. I'll just make sure, because they claim they're like a journalist from France. So I send it over to my colleague in France and a professor in France. So I was like, hey, like, I got this email. It sounds really sketchy, so I'm going to ignore it. And she was like, no, it's a real it's the most popular science magazine in France. You must reply. Oh. So, of course, I did this interview in English because I don't speak French. But I love it because it looks like I speak French. Because look at that quote, right? But I'm okay. So when you do these popular press interviews, the journalists will it's quite timely, so that they will write it up, and they're like, okay, can you just look over for factual accuracy, and they give you like an hour, a couple hours to look over it before they hit press and send or something. And she gave me this, and she was like, does this work? And I was like, yeah, sure. So it's very hard when it's in different language. So yeah, so this is some of the great things we've discovered so far. That was our recent result, but here is me with all my collaborators, right? So this is a high school collaboration. This is a while ago when we had a meeting in Berkeley, my alma mater. So I like this picture. This was somewhere in Italy. I don't remember. We have a lot of conferences and all over Europe. This happens to be Paris, which I like, but usually I'm in Germany, which I'm kind of tired of. I do a lot of outreach talks, especially to young women and girls. That's kind of been my thing. So I have a lot of ways. You guys were talking about outreach and education, and I really believe in that as well. One of the things I really try to hammer home when I talk to young people is, look, like, you might think physicists and think Einstein or Big Bang Theory characters, but look at me. I'm like a normal middle-aged woman, and if I can do physics, you can do it too. You can do whatever you want. You don't stereotype yourself, right? So that's something I want you to So if you have like young women in the family that or girls in the family that you can talk to, you know, there's so many studies that say girls are socially like really subtly not encouraged enough to stay in science and math, and this is something near and dear to my heart. So I think about that a lot. So I do a lot of things. And I think this is my last slide. So if I want you to take away anything from my talk, it's this. I see there's like this cool particle physics detector that can do astronomy and make discoveries that mean something to astronomers. And neutrino astronomy is this new field that's starting, and multi-messenger astronomy. I didn't tell you about this word. This is a buzzword that's been around for a couple of years now. Multi-messenger astronomy, not just like other messengers, other particles telling us what the universe looks like, right? Put it together. This is exactly what the alien hand thought experiment was. Put it together, you get more. The sum of the parts is greater than the part. I'm not going to try. Anyway, so there's boundaries to astronomy that we're pushing now. I think this is the way astronomy will go in the future. And I hope you found it exciting like I do. Thank you.
I have a lot of questions, but I'll confine them to a couple. Can you sort of categorize different neutrinos for us, depending upon their source, how energetic they are, what you most commonly detect there? And the second part of my question is, we all love the cosmic microwave background view,
Yeah,
but these guys can push us further back in time.
yeah.
How much
Okay.
further?
Okay, these are physics heavy questions. I love them. Okay, so the first one was what can they tell us? What can we tell about the neutrinos, right?
How do you categorize?
How to count it. So we can
Different
tell their
energy
energy. And if I get into a lot more particle physics-y things, which is graduate level, neutrinos have different flavors or types, if you will. It turns out they oscillate. So there's a lot of like physical processes that you can gather from measuring the amount of each population, and its ratio tells you something about the physical processes that happen within like energetic interactions of stars and galaxies and other sources. So if you have the energy spectrum, if you can measure the energy, you can measure the energy spectrum. And this is like spectroscopy in astronomy, right? But only with not light, with neutrinos. So you can do spectroscopy with neutrinos. You can do this sort of species population game. And what all that gets you is that, you know, different sources probably have different creation and emission mechanisms of high energy particles, including neutrinos. So the more you can measure about the characteristics of neutrinos, like you were getting at, the more you can tell about the physics, the energy budget and the physics that happens in, for example, you know, jets of blazars or something like that, right? Or supernovae components. What when the shell of supernovae like go out, right? The shock radiates out. What happens? What is happening in that shock? What is the energetics up there? What particles do what? And how do they interact and how do they escape their environments? All this is vital to astronomy. It is very hard to calculate these things from first principle. In fact, it is impossible almost because the physics is so complex. And so any measurement you can add to any of these processes and any characteristics in any measurements you can add, for example, via neutrinos, it helps pin us the physical mechanisms so much of the source environment. And that's kind of like the future goal. So we're not quite there yet. So I can't give you like a really good example of, oh, and we measured this star and we discovered this. We're not there yet. But hopefully within our lifetimes, I want to come back and say like, hey, it turns out neutrinos come out of this, I don't know, maybe the Crab Nebula even, right? And I'll add another picture there and I'll tell you what that means. Like that's kind of where we're trying to head to right now. So it's still in its infancy. You had a second good question. Oh, cosmic microwave back. Yeah. So if you don't know what that is, the cosmic microwave background is leftover light from the Big Bang. So what happens is whole universe was the point, you know, everything started to expand, right? So whatever was there, how can I explain this? It's really technical physics that I'm trying to explain.
The first one in the universe.
Yeah.
The opaque thing when there was
Yeah.
nothing but plasma
Yeah.
started to condense into particles and
Yeah. So it's like when you have a really energetic kid that likes to run around. And you confine him to like inside because it's snowing outside. And he's like, ah, I have a little son. Right? If he's super energetic, right? That's big day. Like that's like the universe is small. And then like all of a sudden it's a sunny day and you release him to the outside and there's no more boundaries. And then, you know, the universe is his and he can run around and then his energy goes down, right? Like everything relaxes a bit. So the light in the early universe was confined to such a tight space. And when the universe expands, the energy, you can think of the energy density becoming lower because the volume gets bigger, volume of the universe, right? So what happens is all this light with high energy comes lower and lower energy, which in terms of redshifts. So ultimately, here we go. It goes all the way, right? So now we're down to microwaves. So it's very stretched out. So longer the wavelength, the lower the energy. All right, so this is the leftover light from the universe that has cooled, if you want, significantly. What it means is that it's very low energy, so it's very hard to measure, and there are many dedicated measurements that produce spectacular maps of this. In terms of neutrinos, so that's this side. In terms of neutrinos, we are a very high energy neutrino measurement. And so what we're looking at is probably nothing to do with the early universe because everything there is cool. But the most violent things happening now, and I say now in quotes because again, right, it takes light years for anything to travel between us. But so now here's the kicker. Oftentimes when I give this talk professionally, I say like, why don't we just do it in light? Like we want to look at the high energy universe. The highest energy light you can use is gamma rays. Why don't we just do gamma ray astronomy, which is a legitimate field and very interesting field? The thing about gamma rays is that it actually is so high energy that it interacts with the cosmic microwave background, and it makes the universe opaque to gamma rays. So this is another reason why I say we need other messengers other than light, especially at the high energy end. So this is high energy end, low energy end. But the high energy end, if you want to understand the high energy universe, you can't just rely on light because of the cosmic microwave effect. And then it becomes a particle physics argument why these two extremes interact with each other. And that's another thing, like then you get a timing diagram. So I can't really explain that.
Beginning of the universe, there must have been lots of neutrinos, really.
Yes.
Where are they today?
So there is cosmic neutrino background. It's the very lowest energy neutrinos. It fills everything, even this room. It is so low energy, there's no way we can detect it. And some of my colleagues, particularly some experiments. And so if you want to look up experiments, I think it's called Ptolemy, the newest one, or Project 8 is another one. So some of my colleagues at MIT have like this wild ideas using semiconductors to see interaction of leftover neutrinos from the Big Bang, which is the lowest energy neutrinos you can come up with. So that's on this side, we're on that side. Yeah, neutrinos fascinating on either end.
So again, another like cosmology related
Mhm.
question. It's probably dated now, but I thought like years ago, the thought was neutrinos and dark matter have they're independent, no interaction. That's still the case, especially as you've studied more and you've identified high, or is there now interaction? Because I would think that would have pretty significant consequences, right?
Absolutely. So AI, you can ask me what I need at the South Pole. It doesn't have to be this kind of intelligence.
It's true.
Question, by the way, I should know because because we've been very like seminar level questions here. I can talk about like what it's like to live here too. Right, dark matter. So we originally said the universe has to have more matter than we can see. So we named it matter because we're not very original in physics. So we are looking for missing matter that we can't see. And by can't see, we mean that they don't interact. So I talked about interactions a little bit about neutrinos and how they rarely interact. So for a long time, like decades ago, we thought neutrinos could be a dark matter candidate. It turns out it's not interacts too much. The mass is not enough. There's a lot of things about it that don't make it dark matter. They're not cold enough. Essentially, they interact too much is the answer here. But so then people thought about dark matter neutrino interactions, and we do have a group in our collaboration of 400. Some people, maybe like 5% of them, very interested in looking for neutrinos from dark matter interactions. And in the universe, dark matter tends to, well, we think, I should preface this. We think dark matter tends to clump where there's a lot of density. So like really compact objects in the sky, you know, galactic centers, even like in the middle of the sun, in the middle of the earth, we think dark matter sort of has a high density. Lots of dark matter tend to clump there because they're gravitationally attracted to each other, I guess, bound to each other and of normal matter. And then if there's interactions of dark matter that go to neutrinos, you can look for that using our telescope or detector. And there is a very small but active group looking for that. So people still do theorize dark matter to neutrino interactions quite a bit, actually. But a lot of that is unconstrained by experiments. It's another way to say there's just wild theories that we can't disprove. Yeah, I'm sorry, I'm a little honest sometimes.
What?
I have a question, if you can hear me.
Absolutely, go ahead.
Right, a question about Ice Cube. In astronomy, in optical physics, we talk about, the field of view and angular resolution of telescopes.
Yes.
What's the analog for Ice Cube?
Oh, I love this question. And again, you can ask me what I eat at the South Pole. I want to emphasize that it does not be this high level and technical. I am here to give an out shot. Okay. Yeah, but since you guys insist we talk at the seminar level. So because I told you neutrinos go through everything, and remember that flashlight, I said if this was a desk and I had a flashlight, the light doesn't go through, but neutrinos go through, right? So imagine this is a star galaxy with light and neutrinos emitting. Imagine this desk is the Earth, right? So if I stand here on Earth, I can't see stars that are other side of the Earth, right? And then, if I dig here, you get to the other side of the Earth eventually. Then there's a sky. Then there's outer space, right? And I cannot see starlight from that star. However, neutrinos go through everything. So I can see neutrinos from that. So
you actually get neutrinos then coming like through the Earth from the North Pole direction?
Our field of view is 4 pi. It's the whole sky.
Okay, 4 pi, okay.
Yes. It's the whole solid.
And so when you have neutrinos coming in at a shallow angle, then you have to be able to correlate how the different sensors are activated. So you have some type of scanning mechanism to be able to correlate that?
Yes. So the reason why it's a grid and not a flat plane or a tube is because we can expect neutrinos in any direction, through the Earth, up from the sky down, like you said, grazing the Earth, any direction. And so what we have is these sensors have extremely accurate timestamps. And so we can tell, I wish I had a movie. We have these movies where you can see like this lights up, 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 this lights up. And by light up, I mean see the light. And you can tell it's because there was a particle going through like this. And as the particle goes through, it emits light, right? So it's like Cherenkov, right? And then you can see the light source moving across. So even though you can't see the particle itself, but it's small, they're elementary particles, you see the light sort of like source moving across our detector. And that's how we try to say, this neutrino came from that part of the sky, this part of the sky, that part of, 4 pi. So any part of the sky through the Earth, so you can come from. I spend a lot of time doing this, a lot of time thinking about this because, as you know, in astronomy, right, the sharper image is always better. Yeah. What does a sharper image mean? It means, right, so if you have bad eyesight, if you're nearsighted like me, right, and you look at the sky without your contact lenses, it looks blurry. right? If you see a star, if I can barely make out a star, then it'll be like, well, there's this fuzzy thing, there's light coming in from there, there, but I think it's really just one point, right? A sharper eye means that, like when I put my contact lens in, there's a star there, I can tell because there's light coming from just that direction and nothing around, right? So what that means in terms of neutrino astronomy in our telescope is that the better you can get your angular resolution. So now, the neutrino came from that plus minus, is it this part of the sky or plus minus this part of the sky? Those two things create a very different image in terms of sharpness. And I spend a lot of time in usually actually nowadays using machine learning, artificial intelligence, try to make that error circle as small as I can because it relates to the type of astronomy you can do, how well you can do astronomy. So that is something near and dear to my heart. It's a very good question.
So
Thank you.
just a little bit.
Yeah.
What kind of, you're clearly, the way you designed this, you're sifting and sorting out
Yes.
the lower energy ones, when you're looking at a particular
Correct.
energy level of
Correct.
neutrino.
Correct.
These energy levels that we're looking at, of the billions of neutrinos that
Yes.
go through this thing probably every minute,
Yes.
how many hits, how many signals we get?
Yes. Yes. So I brushed a lot of physics under the rug. So it turns out we have a lot of background, but not neutrino particles going through our detector, and those things we have to filter out. So identifiably neutrino particles, I would say about a couple hundred to a couple thousand a year.
That's really low resolution.
It is very low. We've been running for 13 years straight, 14 years straight on 24/7. Detectors never down, always taking data.
You got like maybe 30,000 hits.
That is identifiably neutrinos. Now, identifiable is the question because, okay, so now I have 30,000 things that I know are neutrinos. Now I have a different pile of stuff where it's like maybe 100,000 stuff. And maybe I know that 50% of these are neutrinos. I just don't know which 50% yet. Do you add that to this bucket? Does it help you? Yeah, for some things. Then I have another bucket that's like maybe a million things, a million particles. And I know like 30% are neutrinos. I just don't know which 30% yet, right? So my job is to sort it into these buckets and see which buckets to combine to do the best physics I can do. And that's kind of one of my things that it's
On that subject that you're trying to.
yeah.
Okay, being that this thing is total darkness, you pretty much rule out optical light.
Correct.
Okay,
Correct.
so the thing that you're trying to filter out, spontaneous fission, what?
It's actually cosmic rays. Cosmic components from the atmosphere.
They can actually get that deep. Yep.
There's one particle that can, it's called a muon. So every single particle physics experiment suffers from a muon background rate, and ours is no exception. And this is why a lot of other particle physics, they're in like caves or mines or deep underground. Like if you ever heard of CERN, this is the particle collider. They don't do it on the surface, they kind of do it underground. Yeah, everything you want to do with particle physics usually underground because the atmosphere, because of cosmic ray bombardment, usually produces so much muons. And these mimic neutrino signals so well. And this is irreducible background. So the one thing that we have going for us is that these muon backgrounds are uniform. So if I look at the sky, right, it's sort of the analogy I like to use is like you're doing astronomy in downtown Philadelphia. There's a lot of light pollution. There's a lot of light that has nothing to do with your starlight. The good thing is they don't look like a star because a star is the point in the sky and the background light is just this diffused light that's everywhere. So it's the same thing. I'm trying to do neutrino astronomy in downtown Philadelphia-ish, except you can't get away with dark sector. You just, everywhere on Earth is like this. And you just have to develop statistical tools to do that kind of like the buckets I was telling you about. The angular resolution helps. Like I was saying, if I could pinpoint all these things where they're coming from super well, then I know that if a lot of things piled up in this part of the sky, there's a star there. So this is the type of statistical games we play. The data analysis on this experiment is very challenging. And again, this is where all these particle physics skills come in. This is not quite astronomy, right? Because astronomy is like point, shoots. This is what we saw, right? Like, I mean, no offense, I mean, launching Hubble is really hard. No, absolutely, like, right? I can't imagine. But you launch, you open, and you see, wow, so beautiful, right? We made ice cubes. We started data taking, and we're like, wow, that's a lot of noise. Okay, we better start analyzing all this, sifting through all these things to find our signal. And it's like that. A lot of particle experiments are like that. We operate in a high volume, low signal to noise environment. And it's all in this statistical analysis we can do using the particle physics knowledge that we have.
So setting up another ice cube on Enceladus and some other ice moon out there isn't necessarily going to increase the resolution, please.
So I'm on another project. This one is going to be an ocean off the coast of Canada, then Vancouver Island in the Pacific. And we're trying to do it in water.
What do you eat there?
Hmm?
What will you eat there?
You know what I eat on Vancouver Island, but not that's how. Yeah. I mean, okay. So just to give you a chase, what do I eat at the South Pole? Because nobody's asked, I'm gonna ask myself. It turns out the fuel cost to ship anything to the South Pole is so expensive that it doesn't matter what the material costs. So we get fed very well at the South Pole. And this is the same as, I don't know if there's any naval officers here, or Navy people here, but it's the same in submarines I hear. Where, you know, storing food, the depot of food is so difficult in submarines. Keeping up the food cost is not that much of a consideration. In fact, if it's morale boosting, it's better to have good food on the submarine. Same thing itself. So we are fed very well. The one thing they can't do is it's very hard to keep things not frozen. Things that freeze well, like lettuce. Oh my god, lettuce never tasted so good. Don't freeze and thaw out well, don't do well. Another example.
What-
Really
What do you have to study to do your kind of work?
Oh, that's a great question. So I can tell you a little bit. So usually when I go talk to schools, I do a little bit of like, how did I get here kind of thing. So I studied physics. I studied physics in college. And in high school, when I was figuring out, oh, what do I want to study in college? You know, I don't come from a very academic family, so, you know, I understand what studying engineering meant. You study engineering, you become an engineer, right? And, you know, my parents were like, well, you study, what do you become? A physicist? And I was like, haha, yeah, I know what to become. And in terms of the answers, you can become many things as a physics major. Same with math majors. You can become a lot. But here's the thing, and I know this sounds a little bit tone deaf in the current climate, but it's very important that you have a time in your life where you study things because you find it interesting, not because of something that happens later or you're trying to get ahead in life or any practical reasons. Intellectual curiosity is a gift, and being able to somehow afford a couple of years, even if it's 2 years, to pursue that intellectual curiosity in like an astronomical society, if you will, later in life even, but even in early in life when you're in your teens, to be able to have the opportunity to pursue things just because you're interested is an amazing thing. So I studied physics because I was interested in physics. I didn't think I would become a physicist. I actually didn't even know you could become a physicist. I just studied physics because that's what fascinated me. And so you sound quite young. So I just want to say that whatever you find interesting, keep finding that, right? Treasure the things that you find interesting. Curiosity is a hard thing to teach. And it's very easy to become uncurious. I think curiosity is really important. So yeah, that's my sort of short, long answer.
I have another Ice Cube question, if you
go.
can. Right. So this is like a Ice Cube is is always on. It's always collecting information. It's staring, right, all the time. Do you ever see? So over time, I would assume that it's you can integrate that and get some nice information. But do you ever see any events You ever see events like neutrino bursts or anything like that? Can that
Oh,
be
that
detected?
is, you have no idea how good of a question that is. Yes. So we are a great burst monitor in the sky because we see the whole sky all the time. In fact, the last, I want to say 10 years, a lot of our efforts have been monitoring of these neutrino bursts. And if we see any candidates sending out astronomers' telegrams, ATELs, or notifications to our, normal telescope folks, right? And say like, hey, we think there might have been a bang in neutrinos over here on this part of the sky. Can you point your telescopes? Because again, like you were saying earlier, telescopes have a field of view that's quite narrow, right? So if you're not seeing this part of the sky, you're looking at some star over there that's very interesting. There's no reason to point to here unless somebody like us, we say, hey, astronomers all over the world, we think there might have been something going on here in neutrinos, that we saw a flare of neutrinos in this part of the sky. We don't know if it's true or not. Can you check with your telescope? And some telescopes have dedicated time where they call neutrino follow-ups, right? So they have a certain amount of time where they will prioritize following up on our telegrams. But then they're not real telegrams, they're emails, they're alerts, but they used to be telegrams, so it's astronomical telegrams, right? So then some telescopes will interrupt what they were observing, point it to that part of the sky, and then in another telegram say, yes, we do see some activity there, or no, I don't think that was real, right? And in fact, one of the earliest interesting neutrino sources, which was a blazar. A blazar is a supermassive black hole with a jet coming out, and that jet has to be pointed at us. That's what my astronomy friends tell me. There was a blazar that we saw flaring in neutrinos and in normal optical telescopes at the same time. And that was like one of the first discoveries that we've published as a discovery. So yeah, bursts super important for us. Absolutely. Absolutely.
Thank you.
Yeah, great question. Yes.
What are some like interesting things you saw with a telescope that you can't see with like a regular one?
Oh, that's a good question. So we whenever like a physics department colloquium or something like that, I always end with that. I always say, gosh, wouldn't it be great if we discover sources in the sky, galaxies we couldn't see before in any other way, because the light can't go through the dust, right? Maybe there's just so much dust and we never know there's a star there or a galaxy there unless we use it with neutrinos, and it's dark and everything else, but it glows in neutrinos. Wouldn't that be great? And so I would love to come back and tell you when we found something like that. I don't have any examples like that right now, but that is usually what I end on, because if you think about the possibilities of what the universe looks like in this new way, right? It's almost like, you used to be like, I don't know, maybe colorblind and now you see color, right? Or you know what I mean? Like it's a different way to look at the universe. And if we see something we've never seen before, wouldn't that be fantastic? So I love your question because that's my question too. Yeah.
Thank you.
Yeah. Yeah.
Talking about resolution before. Yes, I'm wondering, you have this, type.
Mhm.
You ever try to maybe, I mean, like in radio astronomy and optical astronomy, you think of this parameter.
Yeah.
You can increase your resolution by,
Yeah.
you have, I know there's like a big detector in Japan, and one, there's several detectors.
Yes.
Guys correlate your information to see if maybe you saw something, you saw a hit, and somebody else saw something coming from kind of the same direction.
Yes. Yes. So there's two answers to this. One is absolutely yes. So we talk to other neutrino telescopes, we talk to other telescopes of every kind. We look at sub-threshold events, which is to say, like, we don't want to claim we see something here, but maybe there's something there, right? And if full other telescopes have this at the same spot, and again, if it's at the same time, then it becomes interesting. So we have these like private communications as well, not on like ATEL or anything public. And we try to correlate things, and this is absolutely something that's the first answer. Second answer is for interferometry. So interferometry works really well when you're on this side of the wavelength. So anything low energy, like radio waves, gravitational waves also have very long wavelengths. They're low energy signals. Neutrinos, the neutrino astronomy we do is on this side, high energy, right? Short wavelength. But the interferometry might be interesting for, we were talking about primordial neutrinos, cosmic microwave, not microwave, cosmic neutrino background. For that kind of low energy neutrino, maybe this is where the interferometry might be interesting. So there's some equivalents. This is called particle wave duality, which is something I also teach in this quarter, where every particle can be think of as a wave, and every wave can be thought of as a particle. So I keep saying like low, like, you know, gamma rays and radio waves, and this is low energy and high energy, and long wavelengths, short wavelengths, but you can do this with any particle actually. It doesn't have to be light. So we think about this as photons, a particle of light. But you can think of neutrinos as having a wavelength too. So yeah, you get into all this messy sort of particle physics stuff, quantum mechanics stuff, but yeah, neutrino interferometry is, yeah, it's interesting. I think it's interesting. So yeah.
Softball question, what do you use for energy here as far as like for your servers?
Thank you.
And how do you get the lights on?
Thank you. Yes. Yes, this is the kind of question I look for. So this is the reason why planes can't take off or land in the winter as well. So it's too cold for normal fuels. So the only thing that you can use at the South Pole is jet fuel actually. It has a low freezing point. So everything runs on jet fuel. So there is a power generator that runs on jet fuel. All the ski mobiles we have converted to use jet fuel. And in fact, every plane that lands carries extra jet fuel and unloads during the summer. So there's enough jet fuel to carry them over the winter. And this is the reason why in the dead of winter you can't land, because once you land and the engine revs down, you can't back up again because it's too cold. So they can do like airdrops, but they can't land up. This is why there's no in or out in the winter. The water we drink at the South Pole Station, you have to use energy so there's ice everywhere, snow everywhere, but you have to put it to water. So there's you have to use again power to melt the snow into water, and so you have to use jet fuel to do this. So there's a constant water shortage at the base. So there's like this I don't know if they still have it, but when I was there's like these TVs throughout the base that tell you two things, like outside condition and how much power we've used and how much water there's left. And it's really crucial, right? So you get like 1 3-minute shower a week at the South Pole. Yeah. So when I went back to McMurdo Station, because they don't have that constraint, because they could have like big tankers and icebreakers come in and deposit fuel. So when I went back to McMurdo Station, the first thing I did was like take the longest shower of my life. So yeah, so water is a scarce resource because it uses energy. So anything that uses energy to do anything is very, very scarce. And it turns out water usage is quite a bit of the budget of energy use, so they're very strict on that. They try not to melt the surface ice because it's icky, right? So they have a well where they try to get like clean snow from. So they dig and they get the snow from there. And I don't remember how deep it is, the well, but I do remember that so because at South Pole Station there's snowfall, and then there's snowfall, and then it gets compactified and compactified and compactified. So the lower you dig, the more you're going back in time of when the snowfall was. And so the well depth is at the time of when the snowfall was when Jesus was alive. It's something like that. It's like Jesus water, right? So I remember that real well. Yeah, I don't remember this, but I remember it was snowfall during Jesus. That's all I remember. It's funny.
With the ozone hole in the atmosphere, do you have to do anything special as far as UV protection?
Yeah, they told you definitely. It's actually bad for your eyes. So of course I was there in the summer because there's sun all around. So your skin, you usually, unless you're kind of an idiot like us and like to run around naked in the cold, which we only did once for ceremonial pictures in our bathing years, like the powerful stuff. Fine. We're young, but, and we dress right away. But, so you don't usually have a lot of skin exposure, but what you do have is eye exposure. So it's really bad for your eyes if the ozone, like because of the ozone, there's no, the UV gets straight to your eyes. So you are asked to like put on like eye protection gear if you're outside a lot. So there's that. South Pole Station does a lot of science, not just ice cube. One of the things that it does is it has a clean air sector, so it has the cleanest air on Earth. And since the 60s, I think, they've been flying high altitude balloons to take air samples, and they monitor the greenhouse gas in the atmosphere because it's not like there's no local factories or any activity, right? So, and then it's upwind station. So there's a clean air sector. And since the 60s, every single day, I think they launch weather balloons that take air samples, and they've been measuring the global sort of greenhouse gas concentration sphere. And that's where all those alarming plots come from. It's air measured at the South Pole Station. So, yeah.
This barbecue penguin tastes like chicken. That's just. Final question.
Okay. So I'll answers for you. One, there's something called the Antarctic Treaty. So it's signed by every nation that has activities at the South Pole, or sorry, in Antarctica. Let me go to the right slide. Here we go. So if you go there and you be part of the Antarctic Treaty that says, I'm going for peaceful purposes, and that includes not procuring with wildlife. So there's like this protocol that you're not supposed to, like, even if the penguin is going off to like away from the ocean and definitely will starve to death, you're not supposed to like interfere. You're supposed to just let it walk away. And there's this what's his name? There's this one amazing German director made a movie in Antarctica where he talks about the penguin walking towards the mountains and his face mind state, and it's like this video is just like this penguin just walking towards the mountains, and like researchers are looking at it like, what are you doing here? What are you doing? But you know, it's like this mental state. So you can't interfere. That's one thing. But there are penguin colonies and there are scientists that research that kind of stuff with that. So there's that. So at South Pole there's no penguins. Oh, also thank you for asking about penguins and not polar bears, because polar bears North Pole and Antarctica, right? You can't. There's no penguins in the North Pole and there's no polar bears in Antarctica. So thank you for getting the right animal. They saw shirts in the McMurdo station that has like a no on the polar bear, that's on the penguin. That's the one call. Yeah. And then yeah, so penguins, they're kind of far, so they usually, if they're sane, live closer to the water. And usually our bases are away from the water because we want to be more stable. So I saw one very far away.
If you see one at the South Pole, he's really lost.
I don't think it can make. So there's one animal that has been seen alive at South Pole, and it is a bird called a stool. And it is definitely died. It passed over the South Pole, but it's over the South Pole. So that's how far it is. There's nothing but blood, unless it's re-engineer it that way, I guess. Yeah. Is that a good question?
Thanks for doing it.
Thank you.
Thank you.
That's for the videos.
Yours be sticking right there.
Yes, thank you.
That's one. Thank you. Amazing.
Oh, thank you so much. I hope it looks good. Here we go. Yes, thank you.